Hello. Hi, we'll start. Happy Tuesday. We'll start with exercise, okay? Because it's way to wash my inside of my body. I wash outside of my body 5 days a week by taking a bath before going to work. Okay. How do I wash inside of my body? Exercise. I just ran. I came back from running around my blocks. Okay. So yeah, you have to wash inside of your body by doing exercise, cardio, muscle exercises. Otherwise, fat, sugar, all the bad waste of your body start to accumulate and clog up your artery, vein, your canals, your intestines, okay? You have to exercise 5 days a week, Monday through Friday, okay? Otherwise, you become ugly, okay? Your body become obese. You become unhealthy, okay? You have to exercise, all right? I know Bible doesn't talk about exercise, okay? Because back in the days, they didn't need to. All they did, the chores, work, you were very physical, okay? But nowadays, we have machines doing all the physical labor for us. So that's why we have to exercise, okay? Now, sideways. Oh, oh, oh. Wow, quite a workout. Ooh. Oh. Oh boy. Okay, let's do some stretching. So how many minutes has passed? Less than 30 minutes has passed, okay. Well, and now I'm hot. You cannot make an excuse that, oh, I don't have time to exercise. Oh, I don't have money to exercise. That's all excuses, okay? It takes only 5 minutes to exercise, all right? And it takes zero money to exercise. Actually, it's gonna save money because you're not gonna go to hospital because you never get sick if you exercise regularly. You save money. And you save time too because if you don't exercise, you will get sick, you will get injured, okay? Because your body is so inefficient. And guess what? You cannot work. You cannot work as efficiently as before if you're unhealthy, if you get sick, okay? So you save your time too eventually, okay? Eventually will. It's a good investment, alright? Oh, and then neck rotation. Oh, shoulder rotation. Wrist rotation. Then finger exercise. And the ankle rotation right there. down there. Ankle rotation. Also, I'm balancing, alright? Yeah, balancing is good exercise. And toe exercise, toe bending. The other ankle. Now, we'll do some squat, very light squat, okay? Yes, nowadays, not many American adults can squat like this. And not many Americans can run. Okay, it's such a shame, alright? That's gonna. If I do become the president, yeah, I can change all that shit, okay? If not, nobody can change this. I'm the only one who can change America. I'm the only one who can make America healthy. Again, okay? Or just healthy. Okay? There's nobody else. Yeah, how can I not run for president in 2020, okay? Knowing that I'm the only one who can change America for the better. Hmm? Yeah, that's why I'm running. And I keep on running, okay? Keep on running. Alright, we'll take a break. And we will continue our journey with that, whatever. Okay? Oh boy, it's taking forever. Yeah, we try to finish it up today, alright? The vector summation whatnot. Yeah. So Americans should start to realize exercise is not an option. It's a survival. It's not only survival of yourself, it's survival of your children, your future generation, the entire nation, healthcare system, health, everything, happiness, everything. Exercise is not an option. You have to exercise. Alright? Anyway. But don't get me wrong, I'm not gonna have like sugar tax, gay tax, tattoo tax, piercing tax, fat tax. I'm not gonna do that. Alright? Nah. Taxation, come on. We have enough tax already, okay? We gotta get rid of taxes, not make one. Alright? I have better ways to make money. I mean, to make America rich. I have far better ways to make money because taxation is internal money. Okay, that's not gonna help anything. And you raise tax. What are you gonna do with that money, man? What social program? Come on, nah. Stupid idea. Okay, alright. You know, I don't really wanna do this appetizer stuff, okay? I wanna get through with this. We're gonna erase all this appetizer stuff. Oh, fuck that. We want to get through this, okay? So, we'll talk about those things as we come up again later on. Let's just get through this, alright? So, combinatorial argmax, what is it? We have three compressive stress forces, stress forces, okay? So, it's pushing me around, you know? Now, you want to find a pair that maximizes this theta between the two, okay? That's the algorithm, all right? And then you eliminate them, okay? And then you go to the next, okay? So, we proceed with like -2, we are eliminating. We start with n vectors, right? Then we sum them up. We pick the two, a pair, then maximize the angle between the two. I mean, maximize the cosine theta of absolute value. So it's either very close to 0 degree or very close to 180 degree, okay? So we pair them up, add them up, and we get rid of it from the list. That's the algorithm, okay? And by the way, I bought brand new pens, okay? So I'm gonna switch out these pens. This were totally like wearing out. We're gonna bring up brand new pens, alright? Packaging is so tricky to unwrap. There. Got it. Okay. Solid black. Solid green. Solid blue. Good. That's good enough. One more. Yeah, I like brown. I love brown color. So, but we have to step back a little bit, okay? When we add two vectors, okay, we'll just erase this crap, okay? So, when we add two vectors, all right, traditional notation is what? F3. So you're adding two vectors, okay? F1, F2, and this angle is theta, okay? And then resultant vector is f3, okay? Okay, with vector head, all right? Without vector, it's just absolute value, length of that vector, okay? Now, we know f3 is equal to square root of f1 squared plus f2 squared plus 2 times, I always forget 2, f1, f2 cosine theta, right? But that's only, but yeah, this is a square root notation. You just parenthesis and you put the roof only at the beginning, okay? So yeah, there exists such a notation. I've seen it before. It's not very common though. Anyway, so let me turn on the heater, okay? It's getting cold and let me put on some jacket as well. Turn on the heater. Yeah, I'm drinking a little bit less because I like this concept of work and play. So I do this humanology without drinking for a while, like 30 minutes or so, and then I start drinking. I think it's better that way. It just feels better. Okay, maybe a little bit healthier too. So nobody wants to overwork the liver, you know. Okay, so this guy. Okay, so probably the ugliest vector diagram you have ever seen. Oh boy. You know, the way I look, I know it's not always pleasant, but it depends on the angle, okay? Sometimes, you know, I take a lot of photography, so I'm an amateur photographer, okay? So if you're a photographer, you know angle makes a lot of difference. No matter what picture of things that you're taking, angle makes huge difference. And so lighting, okay? So yeah, anybody's face is like that, okay? Is there flattering angle, unflattering angle, lighting? Yeah, it's just nature of photography, okay? But if you don't like my look, well, I apologize, but there's not much I can do about it, okay? So sometimes I like the way I look, okay? Sometimes I don't, okay? Just putting it out there. Anyways, oh boy. Okay, so F3, okay? So what is F1? F1 is what? R1 comma theta 1. F2? R2 comma theta 2. F3? R3 comma theta 3. What is R? Length. What is theta? Theta is measured traditionally from this rightward x, half of x-axis, okay? This angle, okay? Measured like counterclockwise. That's traditionally theta in the polar coordinate system in 2 dimension, okay? Now, all right. Yeah, I don't know too much mathematics, but I have very solid foundation, okay? And I don't know too much mathematics. I just want to know the basics so that I can apply to humanology. And if we run out of mathematics, we already know we'll learn some more. Okay, no problem. Oh boy. All right. So now this is R3. Okay. What is R3? Sure. Let's write it out. This is same as R3, which is same as F3 vector and absolute value. Okay, they call it norm of a vector, but it's just length, all right, of this arrow. That's all it is. And how about theta? Can we calculate theta? Yeah, we can calculate theta. Okay, we can calculate. But how, can we calculate theta in terms of theta 1 and theta 2? And R1 and R2? Okay, yeah, we can do that. Why? Because theta 1, theta 2, theta 3 is equal to theta 2 minus theta 1. Okay? And then we have this equation. Alright? Now, my question to you is, can we get rid of f1 and f2? Okay? Cosine theta here is actually is equal to cosine of theta 2 minus theta 1. Okay? That's what theta is. Angle between f1 and f2. Okay? So I'm sorry, that's not theta 3. Okay? That's just theta. Theta 3 is the, we have f3, right? That's theta 3, the brand new angle. Okay? Now, what is theta 3? How can we express theta 3? That's a good question. I haven't thought about that yet. Oh boy. Why don't we think about that for a while? Okay. Oh. Probably it's not that pretty. Probably it's a little bit messy. But we don't care. Okay. So probably we'll have to use geometry again. Okay. Which is fine. Is there an easy way to do it? Oh man. Let's think about that, okay? Yeah, I'm gonna use black, alright? Because we're gonna write a lot and we probably have to write a little bit smaller too. Okay? So, we have vector, alright? Let's say this is theta 1, okay? And then we have another vector in blue. This is theta 2. Okay? And then now we have the result vector in green. They look like about this. Okay? It's not 90 degree, okay? This is theta 3. Okay, can you see this? It's kind of light green. Oh my goodness, you can barely see it, huh? Well, I use darker green then, okay? Darker green. Okay, it's theta 3, alright? Now, it'll be, you know what, I keep the pens open, okay? Oh boy. Yeah, it's not quite preserving of pen, but it will save me time, so. this is F3, okay? What is this pen? Blue pen? F2. And then F1. Now, F3 is equal to, getting more confused now, man. F1 plus F2, okay? Vector summation. All right, now, we're interested in the relationship between angles, okay? Now we're gonna use red. This is what we used to call theta, okay? F1, F2, angle between the two, that's theta, all right? It has nothing to do with theta 3, all right? We are kind of confused about that last time, 2 episodes ago, okay? So yeah, erratum, okay? I had to correct it now. All right, at least we got the picture down. All right, so theta is equal to theta 2 minus theta 1, okay? And we call this guy, how about x? All right, angle. We call this guy y. All right. So, and theta is equal to x plus y, right? X plus y. All right. And theta 3 is equal to x plus theta 1, okay? And theta 2 is equal to so the bottom line, we are interested in finding theta 3 here, okay? Theta 3, that's what we are trying to find, this guy. We want to express theta 3 in terms of theta 1 and theta 2 and possibly the length of F1 and F2. That's what we are interested, because we expressed length of F3 in terms of F1, F2, and the angle between the two, theta, right? And what is theta? Yeah, theta 2 minus theta 1. Okay, so let's just rewrite, okay? So F3, okay, is equal to square root of F1 squared plus F2 squared plus 2F1 F2, and then theta 2 minus theta 1, okay? That's the good equation, okay? Instead of using theta, we should start using only theta 2 and theta 1, because theta is like third variable. We don't need that. We don't want that shit, okay? Yeah, you just leave it here, but in the equation, we cannot use it, all right? Because originally we are given only F2. What is F2? R1, comma, theta 1. F2, R2, comma, theta 2. Okay, now what is F3? Yeah, we got the length in terms of F1, F2, and theta 2 and theta 1. Okay, perfect. Now, we want to express theta 3 in terms of F1, F2, theta 2, and theta 1. That's what we are interested. Okay, so we know how to express theta in terms of F1 and F2, because you just put it all over there, and I'm sorry, we have cosine, okay? Then you have inverse cosine over there, and then yeah, we can express theta in terms of f1 and f2. Okay, and even theta 2, theta 1 can be expressible in terms of all the other guys. Okay. My goodness, I gotta think about this for a second. Maybe you already have the answer, but sorry, I have to catch up to you if you are doing a lot better than I do, which is great. I want you to be better than me. We better just start. We are maybe I'm thinking too much. Okay, maybe I should just start diagramming, drawing diagrams, because common mistake programmers make is sometimes they think too much. They should just start programming. you know, just write it down. Draw the diagram and okay. So basically, yeah, we better draw this diagram more correctly. So this green actually is looks more like, I'm sorry. Crazy. You more look like this, okay? Oh my goodness, it's not even green, dude. Oh, what a mess I'm making. Okay. Sorry. I have to redo all this shit. Oh boy. So this is why. Okay. Yeah, it wasn't too bad. Alright, so. This is right angle. That's F3. Ooh. Okay, let's just say f3 squared, f3 squared, we are looking at this triangle, okay, is equal to no, that is it right angle? No, I'm being deceived here. That it's not right angle. No. I mean, it kind of looks like right angle now, but in general, no. This is a parallelogram, it's not a rectangle. Okay, so okay. I put it like this, all right? There is, in trigonometry, there is a more generalized Pythagorean theorem, okay? And that's how we came up with this guy. It follows the generalized Pythagorean theorem. So generalized Pythagorean theorem is when the angle is not right degree, okay? So it's a trigonometric, one of the trigonometric identity, okay, for general triangle, and it goes like this. So cosine 90 degree is 0, right? And that's why it zeroes out, okay? I'm sorry, I'm all over. So we have f1, f2, f1, f2, okay, and which is same as f1, right? And this is f3, okay? And theta here, this is same as theta, okay? So this y is 180 degree minus theta, okay? So you know, cosine curve goes like this, okay? I'm making sure you can see this. Cosine curve goes like this, okay? So cosine pi minus theta is equal to minus cosine theta, okay? Cosine pi minus theta, okay, right here, and cosine theta is just the opposite, you know, only the sign differs, okay? So we use the equation, okay? So f1 squared plus f2 squared plus, we call this angle phi, all right? Which is minus cosine theta, okay? To make this guy true, okay? Yeah, cosine phi is equal minus, okay, we got it, okay? So there's trigonometric identity that says whose derivation is what we did actually. It's same thing. The way we derived this two vector summation formula, yeah, it's same kind of derivation, okay? We're just renaming the angle, okay? There's theta, okay, and there's phi, which is phi is equal to minus pi minus theta. That's what phi is, okay? So if we put phi instead of theta here, it goes like this, okay? f3 squared plus is equal to f1 squared plus f2 squared minus 2f1 f2 cosine phi, okay? When phi is so here you have you have one triangle with three sides, right? If phi is the angle between f1 and f2, I mean in terms of this triangle, then we use that formula, okay? Sometimes, because sometimes it's more convenient to look at it like that, okay? All right, but if theta is the angle between the two vectors that have the same origin, then we use this formula with plus sign in front of 2f1 f2 cosine blah blah, okay? But if phi, this angle is angle inside of a triangle between two sides, then yeah, this formula is handier, okay? So we got that, all right? Okay. Then let's get to work, all right? We are interested in theta 3. That's what we have to find, okay? Now we can erase all this, okay? We gotta make some room, right? So theta 3 maybe I erased too many things. Okay, whatever. We have f3, f2, f1, theta 3 minus theta 1. We got that. So theta 3 minus theta 1. That's x, okay? theta 3 minus theta 1, that's x. And we have two sides here, okay? So f1 squared, so f2 squared, f2 squared is equal to f1 squared, f1 squared plus f3 squared plus is minus 2 f1 f3 cosine x, which is x theta 3 minus theta 1, okay? Well, we came up with some equation here, okay? So, but what we want to do is we want this equation to be using only one subscript, the variable with subscript 1 and 3, I mean 1 and 2, okay? We want to put theta 3 in on the spotlight. That's the objective, the value we want to find, okay? And we have too many f3s here, so yeah, well, whatever. But I think it might be okay because we already know what f3 is, right? What is f3? Again, maybe it becomes a truism, okay? We'll see. f3 is equal to square root of f1 squared plus f2 squared plus 2f1 f2 cosine theta 2 minus theta 1, right? Let's say it becomes a truism, all right? Because we are trying to express theta 3 with everything else, all right? We'll see. Now we can erase this diagram because we are done with geometry, okay? If this becomes truism, we have to think of some different way, and we don't want to redraw this diagram, so well, it's, yeah, we'll just leave it. So, and we'll do the get rid of this square root 2, okay? Alright, so now you have f3 squared, okay? f2 squared. Alright, so f2 squared is equal to, oh my goodness, f2 okay, well, we'll do this step by step. So we have f2 squared minus f1 squared plus 2f1 f2 cosine theta 3 minus theta 1. We just ignore this parenthesis, okay? And this is equal to f1 squared plus f2 squared plus 2f1 f2 cosine theta 2 minus theta 1, okay? Parenthesis. We just put bar up there, okay, instead of doing parenthesis, okay? Yeah, it's kind of interesting exercise. Now f2, this guy cancels out, okay? f2, they cancel out. All right? Then what we have left is f 2f1 squared, okay, is equal to 2f1 f2. Can you see any of this? Yeah, well, I'll close up when we take a break, okay? Okay, so this guy go downstairs. Now this guy needs to go upstairs, okay? cosine theta 3 minus theta 1 bar minus cosine theta 2 minus theta 1. Instead of parentheses, we are using bar, okay? Because it's just simpler that way. Okay, we got it. All right. Now, does this it becomes a truism? Maybe, maybe not. Now we have F1 here, so it will cancel out. Okay. And we can erase these guys to make more room. And guess what? 2 cancels out too. Okay. So we have cosine theta 3 minus theta 1 minus cosine theta 2 minus theta 1 is equal to f1 over f2. That's what we have. Okay. And I think we are getting very close here. It's like this. Theta, now we can express theta 3. F1 over F2 plus cosine theta 2 minus theta 1 plus theta 1, and then we do inverse. Cheating a little bit in terms of notation. Ooh. Inverse cosine, okay. Arc cosine, they call it arc cosine. I don't know why. Yeah, inverse cosine, okay. So that's theta 3, okay, and we're gonna plug in some numbers and verify if this is correct, but we're gonna take a break, okay. And I close this up for you so that you can actually see the actual formula. How about this? How about as a homework, as an assignment, excuse me, assignment for you? Why don't you verify by plugging in some numbers? I'm sorry if I'm treating you like students and or my research assistant, whatever. Sorry. Only if you want to. Okay. Yeah. Plug in some numbers and verify if this formula is correct. Okay. I'll leave that up to you. All right. Yeah. Some easy example. Okay. Like 90 degree, 45 degree, 135 degree. Sure. Yeah. Just and we're gonna do it. Okay. Once we get back from break. Okay. But feel free to do it yourself. Okay. All right. Okay. So yeah, I have a very strong foundation in mathematics. Okay, I mean thanks to Korean education system's emphasis in mathematics. Okay, yeah, we're gonna take a break a little bit. But mathematics, all this is Western invention. It's a Western, like Greek, Greece, algebra from Middle East, yeah, geometry from Greece, and then later on in the Europe, like France, Germany, Britain. Yeah, it's European and Middle Eastern is Western thing, all this math. And Asians, when we were introduced to Western mathematics, we were fascinated. I mean, my ancestors, Chinese, Japanese, Koreans, okay, they were fascinated by this mathematics from the West. We were fascinated. It's so beautiful. So yeah, they started to emphasize education of mathematics because it's just so beautiful and also very very useful in science, engineering, and stuff. So yeah, they emphasize mathematics a lot, and no matter what you're gonna major in college, if you went to Korean high school, middle school, elementary school, back in my days, 1990s, 1980s, then yeah, no matter what major you may have, yeah, you should be very good at mathematics to go to 4-year college. Okay, I'm not sure about America. Probably not, right? Because to just go to a 4-year college, any major, you have to know calculus in high school. Okay, it was mandatory. All right. Yeah, Koreans are in general, Japanese, Koreans, Chinese, they are very good at mathematics. Okay, so they all have very strong foundation. And I was top student in Korea, South Korea, Seoul, South Korea. Okay, so yeah, I have very good foundation, Western mathematics. Okay, so let's plug in some numbers, shall we? And then I will start drinking. Okay. If I got it right, then I will award myself with some drinks. Now, let's say theta 3 is 90 degree, okay? Theta 2, 145. Theta 1, 45 degree, okay? Theta 2 minus theta 1, 90, okay? So cosine 90 is what? 0. All length, they're all 1, okay? 1, 1, okay? Now, what is theta 1? I guess we have a problem, okay? So I cannot drink yet. Theta 1 is what? My goodness, I erased all that shit, so now I have to backtrace all over again. My goodness, what a nightmare. Oh. I must have made some kind of mistake somewhere. Okay? Because we have 1 plus 45 degree. What the hell is that? It shouldn't be that way. Ah, man. So this formula is wrong, okay? So, but it's not too hard to backtrace because we already know what formula to use. We are not that far away from our goal, okay? So, we have degree x, which is theta 3 minus theta 1, okay? We have this triangle, okay, with x, degree x, angle x. We have f3, f1, f2, okay? So, I think I kind of know where I made the mistake. Maybe not. Because in Pythagorean theorem, you have this guy squared plus this guy squared is this guy squared, right? And because cosine 90 is 0, okay? So we have something similar to that, okay? f2 squared is equal to f3 squared plus f1 squared minus 2f f3 f1 cosine theta 3 minus theta 1. Okay, so that's the correct formula. Now f3 is equal to that, so we have f1 squared plus f2 squared plus 2 f1 f2 cosine theta 2 minus theta 1. Okay, and except f3 squared, oh my god, sorry, I'm sorry, except f3 squared, we are passing all the rest to the other side. Okay, and this is equal to minus f1 squared plus f2 squared plus 2 times f1 f3 cosine theta 3 minus theta 1. Okay, that's what we got. We are interested in finding theta 3. All right, so now f1 f1, okay, f2 they cancel out. Okay, so what we have here, wow, we're running out of space really. What we have here is this, f2 they cancel out. Okay, so f1 squared, yeah, we pass it over there, and so you have, and 2 f1 they all cancel out. Okay, so we have f1 is equal to so that guy go over there, this guy over here, f2 let's see, yeah, making too many shortcuts, but we have to because we are really running out of space. Okay, so that's why probably I made a calculation mistake. Okay, but yeah, just hold on tight. All right, we get there. f3 cosine theta 3 minus theta 1, no, minus f2 cosine theta 2 minus theta 1. Okay, it's kind of symmetric structure here, so yeah, I have a good feeling about this. You have 3 minus 1, 2 minus 1. Okay, yeah, it kind of, I'm suspecting this is correct. Okay, now let's solve this equation for theta 3. All right, okay, well, you have f1 plus f2 cosine theta 2 minus theta 1. Okay, I'm just passing this guy over to the other side, and you have to divide by f3. Okay, it may become a truism. Okay, I don't know, we didn't want that, but well, at least it's a mathematical exercise. So, and then plus cosine. Okay, oh, we gotta do arc cosine first. So theta 1 plus this whole thing arc cosine. Okay, so that's what theta 3 is. Okay, now we have to figure out if this ends up being a truism or not. Okay, because then all this for nothing. Okay, hopefully it doesn't become a truism, or maybe it will, I don't know. Okay, so now we can erase this guy. to make some room, okay? We'll plug this guy in, all right? So, theta 3 is equal to theta 1 plus cosine inverse. What is f3? Square root of f1 squared plus f2 squared plus 2 f1 f2 cosine theta 2 minus theta 1. Okay, again we're going to reuse the bar notation because we are running out of space. Close parenthesis. All right, upstairs we have close big parenthesis. Okay, upstairs we have f1 plus f2 cosine theta 2 minus theta 1 bar. Okay, bar same as parenthesis. Okay, now is this a trivial function? I mean, does everything like cancel out and shit? Oh, we don't want that. You know, we're gonna erase this guy, okay, so that we make this equation look nicer. All right, let's just to be aesthetically pleasing, okay, and we're gonna get rid of the bar notation and shit. Okay, so they're both theta 2 minus theta 1. Okay, theta 2 minus theta 1, theta 2 minus theta 1. Okay, and then we have big parenthesis for the square root over there, and even bigger parenthesis for this fraction. Okay, we got it. Okay, and now let's see if this formula is correct or not. And first we examine if this formula is truistic. Does everything like cancel out? Hopefully not. I don't think it does. Okay, okay, it's a fraction, right? So the first part is you have f1, right? So divide by f1 here and divide by f1 here, and f1 squared go inside is 1 plus f2 squared divided by f1. Then you have 2 times f2 divided by f1. Then we have still have that, right? So, and if you divide by cosine theta 2 minus theta 1 upstairs and downstairs, okay, then that guy goes in as a squared inverse, I mean the 1 over cosine squared, and then what? You still have those squiggly things. So I don't think it's truism. Okay, now next step, let's plug in the number. Okay, so okay, what is theta 2? 135. Okay, right, theta 2 135, theta 1 45. Okay, so cosine 90 degrees 0 0. We have 1 1 square root of 1 plus 1 square root of 2. Okay, upstairs you just have 1. Okay, 1 over square root of 2, 1 over square root of 2. That's like I think it's 45. Is it 45 degree? It's been a long time. Okay, yeah. So, oh, okay. I think it's 45. Okay, so you have square root two. Okay, cosine of 45 degree. Yeah, that's one over. No, 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 no. That's cosine. Yeah, one over square root of two, right? Yeah, that's correct. Okay. So yeah. Okay. So cosine inverse of 1 over square root 2, that's this inverse cosine whole thing is 45 degree. Okay. Now theta 1 was 45 degree. So 45 degree plus 45 degree, theta 3, 90 degree. Ladies and gentlemen, we got it. Okay. Yeah, this is not a pretty equation at all. It's a very ugly equation. Okay. Probably that's why no mathematics textbook ever covered this. But we are filling the gap, okay? Ugly or not, it's the right thing to do, and we got it, okay? So this is the equivalent of that, okay? Up there you have you cut out of two vectors in polar coordinate, right? R1, R2, theta 1, theta 2, right? You have nice handy-dandy formula using just trigonometric identity over triangle, right? Yeah, we have that. But nobody ever talked about this, as far as I know. I could be wrong. Okay, maybe somebody talked about it. Maybe there's some simplified, maybe there's a way to simplify this complex formula. I don't know, all right? But I've never seen anything like this. I've never seen, vector summation, this angle expressed with theta 1, theta 2, R1, R2. I've never seen it, okay? And which is quite surprising looking back. Okay, it's something very elementary. Okay, we are not using fancy calculus here. We are using geometry and square root. Just undergrad level mathematics. Okay. Yeah, nothing fancy here, but it is non-trivial. It's quite involved. There are a lot of terms here. It's a very long equation, long formula. I think that's why traditionally mathematics calculus books or physics books just skip this. Maybe put in some obscure exercise problem at the end of the chapter, something like that, for advanced credit. But we got it. So congratulations, and we are going to take a break, and I will start drinking, okay? Because I gotta pat myself on the back, so. Okay, let's take a break. I hope you can see this. Can you read any of this? Oh, yeah, you can. Clearly. All right, yeah, it was interesting and fun. I like doing this. It's very fun. Yeah, algebra and geometry coming together is like a party time. Very cool. All right. We will be back after a break. All right. Oh, congratulations. We made it. It was a long journey, but we have a formula. I mean, it's not very pretty, okay? But it's very elementary concept though. It's important. I mean, a vector, a vector has length and direction. And all the mathematics and physics textbook, they just did only halfway. They went halfway and omit the other half. Direction, calculation of direction. That's wrong. I mean, yeah, it's understandable because it's not pretty formula, and also it takes long time to derive this formula. So to just leave it for what advanced credit, what in college honor student homework assignment. Maybe that's where this formula is sitting. Or maybe this formula doesn't even exist yet. I don't know. I was not on. I didn't take any honor credit class because when I was in college, I was just too busy learning English, man, catching up with the English and take classes. I was just too busy. Okay, so no time for honor credits. Okay, so I didn't do any honor credits. Okay, so let me get some water. Okay, I cannot live without water. Oh boy. So now that we calculated this, we can put it behind us. All right. What we should do next is we'll go back to adding up three vectors. All right. We'll add up three vectors, and then finish this. Okay, argmax. Because we are wondering when we try to derive the generic formula, an algorithm of adding n vectors. Okay, what about angle? I mean, vector is length and direction, and angle represents direction of that vector. Okay. Yeah, we are not talking about angle at all, the direction of a brand new vector at all. So that's kind of strange. Okay, then we realize that in mathematics education, also physics education, this part was totally missing in this basic mathematics, vector calculus, vector algebra, vector geometry. This component was wholly missing, and it's wrong. They need to include this. I'm not trying to be famous. Okay, what I'm saying is, you cannot think of a vector without its direction. It's half of the story, but it was omitted for decades, centuries even, in mathematics education. Something that's supposed to be very elementary was missing for entire time, for centuries. Okay, We just corrected that wrong. We fill that gap. Okay. Just like in economics, Alfred Marshall's mathematical model, it was wrong model. So for more than a century, it was dominant curriculum in economics. It's in every economics book on the cover, demand and supply. That notion is wrong. Okay, we proved that. Okay, not only that, we found a replacement or substitute. Yeah, transactional demand curve theory. Okay, that need to be taught. That need to be taught. Transactional demand curve that we discovered, it need to be taught in every single microeconomics class. And it should be in every single microeconomics textbook because it is the correct theory. It should replace the Professor Marshall's demand curve and supply curve because that's wrong theory. Okay. We are kind of making a revolution here. Okay, if you realize that we are right, and it should be a revolution. Whether it's gonna happen or not, well, we don't know. And to be honest, we don't care. We are just having fun, all right. Let the world go away. Whatever. Whether they appreciate our efforts or not, it doesn't matter. Okay, we are happy as we are. Just found something new. Finding something new. Yeah, we are just happy. Okay. All right. Um, because now I'm thinking like if it's a good starting point, okay, but when we the last time what we tried to do was to derive a formula for length, generic formula. What would be the length of adding these n vectors? Okay, so and we were talking about in terms of compressive force, pressure or like stress. This object is filling. Before we do compressive force, why don't we try to come up with a generic formula of adding n vectors? Just traditional vectors, not like stress vectors, okay? Maybe we should do that first. Because we haven't done it yet. We kind of jump ahead, Ah, boy. Because in traditional vector summation, you don't have to use argmax, okay? You don't have to like pick and choose, and because ordering doesn't matter, okay? So maybe that's the right thing to do, all right? To find an algorithm, okay, let's do that, okay? Because that's the logical order. Well, I have brand new eraser and eraser holder here, so okay. Oh boy. Again, mathematics, that's why I didn't major in mathematics or physics. It's rabbit hole, okay? I mean, I have better things to do in life. I want to dance. I want to sing. I want to do martial arts. I want to run for president. Do politics. Yeah, shop for neckties, and I didn't want to get too much into this mathematics and physics because I like doing it. Okay, but I didn't want to be. I did not want to be engulfed, swallowed up by this ideology of mathematics or physics. Okay, that's why I didn't major in mathematics. Okay, though I could have. Give me one second. Okay. All right. Let's just do addition of n vectors. Ugh. Ooh. Oh man. Let's just do it in algorithmic level first. Okay. So. Okay, in a polar coordinate, right? Does it have to be polar coordinate? It's easier. Why? Because even if we use rectangular coordinate to add up two vectors, to find the length, you have to use theta. Okay, f1 squared, f2 squared, 2 f1, f2 cosine theta. Okay, yeah, you can express theta as arc tangent of y over x, but that's very bulky and very cumbersome and inconvenient. So when we do the addition of vectors, probably it's easier to use polar coordinate. Okay, the equation gets neater and simpler because in rectangular coordinate, the lengths of, let's say you have two vectors f1 and f2. Okay, what is the length of f1? It is square root of x1 plus x1 squared plus y1 squared. It's just too complex to express. Let me show you. Okay, so what is in rectangular coordinate? Formula looks like this: f1, the length of f1, f3. F3 is equal to f1 plus f2, right? The length of f3 is equal to x1 squared plus y1 squared plus x2 squared plus y2 squared. Well, f3 length squared, okay? Plus 2 times square root of x1 squared plus y1 squared times, this is f1, right? f2, x2 squared plus y2 squared times cosine, what is theta? Arctangent of y, oh boy. X2. This is what it looks like. My goodness. You have cosine, you have arctangent, you have y2 over x2. Because this guy is theta 2. Theta 2 minus theta 1. Okay, that's what theta is. This guy, theta. Okay? This guy is theta 2. Okay, in xy coordinate. As you can see, it's just too complex. It's not as neat as just call it f1 squared, f2 squared, okay? Yeah, so polar coordinate system is a lot better than Cartesian coordinate system when we talk about vectors. Okay? And when we do the vector addition. Okay? Because polar coordinate is more geometric than Cartesian coordinate. Cartesian coordinate is more like algebraic or analytical, okay? But polar coordinate is more geometric, okay? It's a lot simpler when we want to express vector addition, because vector addition is very geometric thing. It's like a parallelogram, you know. You have parallel shifting and all that stuff, okay? So yeah, we'll stick with polar coordinate, okay? Okay. You know, at some point we gotta get back to humanology. Okay, we are doing way too much mathematics here. Okay, it's. I guess you can think of it as a nice break from humanology, but still, we are digging toward the magma in the center of the earth, because the rabbit hole is just way too deep. Okay, so before we burn ourselves with mathematics, we gotta get back at some point. Okay. All right. So let's say you have f1, f2, and f3. Okay, f1 plus f2, we'll call it actually f1 plus 2. Okay, 1 plus 2, the resultant vector. Okay, summation vector. Okay, f1 plus f2 is equal to f1 plus 2. Okay, now we are summing this f3 and f of 1 plus 2. Okay, they will be, if you sum them up, it will look like this, something like this, and there will be now f1, not one circle, 1 plus circle 2 plus circle 3. Okay, that's the destination, adding up f1, f2, and f3. Okay, now what's the formula for that? That's what we should have done first before talking about radial vector or stress vector, blah blah blah. Okay, yeah, we skipped one step. So we're kind of backtracking a little bit. Let's do the right thing, all right? Although it takes longer. Okay, so we have, because it's a vector addition, we have to think about length and angle. Okay, length, yeah, is well known in mathematics textbooks. Angle, we just discovered it. Maybe somebody had calculated before. Possibly, because it's not very difficult formula. Okay, and also it's fairly elementary concept. Just angle of a vector after adding two of them. But I haven't seen it in anywhere. Maybe it's in some obscure book, maybe, or maybe somebody's notebook. Maybe somebody tried like 100 years ago, but never published it. Yeah, possible. Okay. Yeah, but yeah, kind of makes us feel good that we discover something. It could be rediscovery, but still, right? Okay. So we want to find some generic algorithm. Okay, so because let's come up with notation here. Okay, the length of this is f1. Length of that is we call it f1. Okay. How about angle of this? Let's come up with a new notation. This what the angled bracket? What's the name of this guy? This bracket, and there's a curly bracket, and there's what is this guy then? I don't know. I'm a second English speaker. Okay, so we'll call this theta one. Yeah, we'll call it angled bracket. Okay, because I don't want to look it up. All right. Okay, this is just absolute value. Okay, theta 1 is the angle, the direction of this vector. Okay, so we have theta 1 here. You have theta 2 here. This guy, we call it theta of this guy. We call it theta of 1 plus or equal 2. Okay. Now I better start using different color. Of course, this guy is, theta 3, right? And this guy here, from here to here, we call it theta 1 plus or equal 2 plus or equal 3, okay? Now, we want to find a generic formula for f sigma circle k is equal to what from 1 to n, that f, okay? The resultant vector of summing n vectors, okay? Now we have sigma circle in the index level, all right? That notation probably is something new, which I haven't seen it. Or maybe it exists somewhere in obscure mathematical literature, but we want to find that formula, all right? Compressive force, we may pursue that venture, or we may abandon it, at least for now, okay? Because we have more important things to talk about in humanology, okay? And in English expression, yeah, bigger fish to fry, right? There's some, we may get back to that later. That stress force, okay? But for our purpose, we now know enough about how stress works on an object, okay? Maybe we'll leave that, because it's all recorded, what we have done, what we started, but we may not finish it. We can just leave it to some other people, okay? Engineers, mathematicians, physicists. Let them do it, okay? Because our main goal is humanology, okay? We are not here to do mathematics. No, we do mathematics because it's entertaining, it's pretty, and also it helps humanology, okay? Our goal is humanology, to model human phenomena. That's our number one priority. Mathematics, physics, we can leave it to mathematicians and physicists, okay? Because that's not our goal here, okay? We may abandon it, but this guy, maybe we'll abandon this too. We'll just, at least we'll write the formula here, okay? So F, the resulting vector of summing up, adding up all n vectors, we're gonna write notation like this. Sigma circle, because plus circle, right? K is still in the index level, subscript. K is from, so you have now index of index, okay? Subscript of subscript, so to speak. K is 1 to n, okay? K, okay? 1 plus circle, 2 plus circle, 3 plus circle, blah blah blah, and that is equal to f1 plus the vector summation, blah blah blah, plus fn plus, okay? What would be the formula of that? We did enough. I mean, we came up with a recursive function, right? Like, it shouldn't be that difficult, okay, to express this in a recursive manner, okay? So, yeah, you add out of n, you pick the first two, because, you know, traditional vector summation, ordering doesn't matter, okay? Only in compressive, like stress force, when we calculate the ordering doesn't matter, okay? And also, what force comes first, that matters too when it comes to compressive force, when we calculate stress, okay? Yeah, it's a brand new discovery, but we will let physicists, engineers, mathematicians figure that out, because we don't want to get too deep into realm of physics and mathematics and engineering, because that's not our job. Okay, we are just giving them some problem to solve, and we give them hints. Okay, hopefully somebody pick it up, because our job here is doing humanology, and we are allowed to talk about in humanology. Mathematics, we don't need to know too much. We just need to know enough so that we can model some human phenomena. All right, and we know more than enough mathematics than we need to model humanology called phenomena, because humanology is very beginning, it's very elementary level now, because how long is the history of humanology? Less than 1 year. Okay, we started this last August. Okay, so the very beginning stage, so we don't need too much mathematics. Maybe later on, maybe a decade later on, yeah. But we know enough mathematics now, okay, and physics. So, okay, yeah. So come up with some recursive formula, like, okay, you out of m vectors, you choose the first two, right? F1 and F2, right? Now, next, you have sigma k is equal to from 1 to n minus 2. because you had summed two vectors out of n vectors. Okay, so yeah, you now have n minus 2 vectors to worry about. Yeah, it's a recursive function, recursive definition. Okay, and we did that when were doing the stress formula. Okay, so stress force. So we're gonna stop here because this rabbit hole is going like forever, and we want to control ourselves. We want to be in control of ourselves. Okay, so mathematics, it can be addictive. Physics can be addictive. Okay, so we will not let mathematics devour us, consume us, take advantage of us, swallow up our life, our time. No, because we want to be humanologists. So thank you, but no thank you. Okay, so we'll get back to humanology. All right, we'll get a grade. And of mathematics, yeah, it's been nice fucking with you. It's been nice dancing with you, mathematics, physics. Okay, but bye, because it's time to go. Okay. All right, because yeah, we're kind of metaphysically promiscuous. Okay. Yeah, we danced with mathematics for a while, but I don't want you anymore. Go away. Okay. So we're gonna take a break. Okay. Yeah. Feel free to say farewell to this. Okay. Very pretty picture. Looks like this Asian fan, foldable fan. Very pretty. Yeah. Say goodbye. Okay. Because we're gonna erase this shit. Okay. So it's very pretty picture. Maybe I should take a picture of this. Oh well. It's being recorded, so I don't think that's necessary. Okay, so we'll take a break and we'll do humanology. Okay, we're gonna erase all this crap. So, all right. Okay. Oh man. I'm gonna take a picture of this. Okay. It's kind of pretty coloring and looks like this Asian fan, foldable fan, and it's uh, Western mathematics. So there, I took a picture. Then now we can erase this. Okay, we got a lot to talk about in humanology. So I was reading this biographies of several mathematicians and like Dirichlet, Fourier, Cauchy, Galois, Abel, blah blah blah. Right. So Fourier, like Fourier transform, Fourier series, is something extremely beautiful. Ooh, yeah. My first encounter with Fourier is, I mean, as his name suggests, he's French. Okay. Yeah, he's like a contemporaries of Cauchy, and Cauchy-Schwarz inequality. You know, Cauchy stress tensor. You know. So Fourier was his contemporary, so and also contemporary of Galois and Abel. Abel. Maybe not Abel, but Galois. Abel was kind of, I think they were kind of contemporaries, but Abel discovered that unsolvability of fifth and higher order polynomial in terms of radicals. He solved that first, and the Galois came with his Galois theory, and it was kind of he independently arrived at the same conclusion. But so Abel group, Galois group, okay. So they use group theory, okay, but they're kind of independent to each other. Both mathematical prodigy who died young, very sad. So Galois, this guy, you know, French guy, as his name suggests, Galois submitted his paper to Cauchy and Fourier, who are way up there, you know, like editor of top academic mathematical journals, okay, who decide what to publish, what gets published, okay. Fourier and Cauchy, they're way up there, you know, seniors, establishments. Okay. Establishment is not always bad. It's not always bad. Okay, don't be always anti-establishment because they're seniors. Okay, so they made contributions and okay, like parent figures. So Galois submitted his, I think it was Abel. So Abel submitted his paper to Cauchy. He didn't take it very seriously. Okay, so both Abel and Galois, they published to academic journals, you know, very low-ranking journals. Academic journals is just like science, mathematics, it's just like politics or religion. Okay, it's all the same. There's a hierarchy. Okay, they're very top-ranking academic journals nowadays. Science, Nature in America, right? Whoa, what Cambridge Journal of Medicine or whatever. Okay, yeah, top-ranking journals. Or in law school, there Harvard Law Review, Yale Law Review, Stanford Law Review. Okay, yeah, they're famous, top-ranking academic journals, academic magazines. Then there are middle and there are low level. Okay, so Galois, Abel, they probably published in the low-ranking journals. Okay, because they did try top-ranking, but they got refused. Okay. And just like in film festivals, yeah, there are the Sundance, you know, South by Southwest, or New York Film Festival, Los Angeles Film Festival, San Francisco Film Festival, and they're more local level, right? Yeah, I submitted to all different levels, 50 different film festivals after I made my movie. Okay, top level, middle level, they all refused. Only like five of the local level, I don't want to call them low level. Yeah, local level, they accepted my movies, okay? And I'm eternally grateful that they did. Okay, two in California and two in Europe and one in Australia. Okay, I'm eternally grateful. Okay, the fact that they chose my film to show to the public, it means a lot to me. It means the world to me. Okay. So yeah, Abe Galwa, I guess I'm kind of like them. Of course, I don't want to die young. By the way. So yeah, okay, and I guess they kind of later on kind of rediscovered something like that. I don't know. Like Franz Kafka, Spinoza, yeah, they all, uh, both of them I think died young, and they got famous posthumously after they're dead. Kind of rediscovered, you know. Mendeleev, Mendeleev, he was famous in his own lifetime. Okay, he got some good position. He became professors and whatnot. Mendel, he kind of got famous after he died. Okay. Einstein, yeah, he was not in academia. He was a patent clerk. I'm positive that he tried to get researcher position or professor position in some university after his PhD in Swiss. Okay, but probably he didn't get it because his grade level was kind of low. PhD, maybe his dissertation quality was not very good. So yeah, he got a job as a patent clerk, a government agency job after he got his PhD. Kind of abnormal, kind of loser like. That's Einstein, okay? He also failed the entrance exam once, I think. I mean, from what I recall, okay? To go to college. He was not the brightest student, alright? So yeah, but Einstein, as you know, yeah, he became very famous during his lifetime. How about Schopenhauer in philosophy, German philosophy? He was kind of underdog for a long while, and in his time, I think he got professor job, but he had this lecture and this one or two students in his classroom. Okay, most people went to Hegel, another philosopher, famous philosopher in Germany, probably in 1800s. Okay, so yeah, Schopenhauer didn't like Hegel because all these students went to Hegel's class, but not to his class. So yeah, Schopenhauer was a very very long time, very underdog kind of guy. I mean, yeah, history have examples of that underdogs who become famous later in life, like late bloomers, or underdogs who become famous after they are dead. Typically, very brilliant scholars who died young. Okay, and some brilliant scholars like Riemann, mathematician like Riemannian geometry, he died young too, but he was famous during his lifetime. Okay, we have all kinds, all enumeration, all sorts of people, brilliant scholars. Some died young and they become famous after they're dead. Some live very long and they become famous when they are young or when they are old or after they are dead. We have all kinds of brilliant scholars who get recognized eventually. And when I read the history of philosophy, these are two-volume books that's translated from German to Korean. I read that when I was in high school, just out of curiosity. It was not a class. No, I just bought it and I read it. And I took it with me when I came to America after I graduated high school. Okay. I think that philosophy professor who wrote those history of Western philosophy, I think he's a professor in Heidelberg University in Germany. Okay, that's what I remember. Okay, he's a very prestigious uh, university in Germany, like Göttingen, Heidelberg. In France, you have Sorbonne in letters, and in science, you have École Polytechnique, which is like number one, École Normale, which is like number two. Okay, whatever. So Galois applied to École Polytechnique in France. He got rejected. So he applied to École Normale, which is also a great university, and he got accepted. Okay, so I think he graduated from like baccalaureate, bachelor's. Okay, but he didn't do PhD. But I think because he died very young, 20. Abel died when he was 25 or something. Yeah, so they become very famous after they are dead, and because what they wrote in just papers and they did submit to academic journals, it's just too ununderstandable, inscrutable. My goodness, what the hell these young punks are talking about? I mean, they're not even PhDs. What? Not sure if PhD existed back in the days. Okay, not sure about that. Maybe it's backward anachronism. I don't know. Okay, so yeah, I'm just sharing with you what I learned. So Fourier, was it John Baptist Fourier or something? I don't know. Fourier is a mathematician. Okay, he's a very interesting figure. I think he's in 1800s, maybe during the era of Napoleon, maybe. So Cauchy, Fourier, they are also very political figure, a little bit. Okay, yeah, politically conscious, just a little bit, maybe. Okay, I mean like Lagrange, Laplace, yeah, kind of politically conscious, maybe a little bit. Probably there in the days of in the 1800s, probably before Fourier or Cauchy. I don't know. Okay, I don't know the details of mathematics history in France, but also there are some lawyer mathematicians too, like Fermat. Fermat was a lawyer, I think. Was Laplace a lawyer? I'm not sure. Let me look it up. Laplace. You like Laplacian. Yeah, Lagrange, Laplace, they were French mathematicians. Okay, so I know Fermat. Fermat's last theorem. I think he was a lawyer. Okay. How about Laplace? Was he a lawyer? Not sure. Oh, you're an astronomer and mathematician. Okay. So he was in theology a little bit. Okay. Yeah, I don't think Laplace was a lawyer, but I think Fermat was. Okay, so Laplace is just who's D'Alembert? That name rings the bell. Yeah, okay, he's a mathematician too. Physicist, philosopher, okay. What is he famous for? D'Alembert. Okay, mathematics, physics, whatever. Okay, how about Fermat? I'm pretty sure he was a lawyer. Yeah, he was a Pierre the lawyer. Pierre the Fermat. I said Pierre the lawyer. Oh, that's funny. Yeah, he was a lawyer and also kind of amateur mathematician. Okay, Pierre de Fermat. Anyway, yeah. So Fourier was interesting figure. I think he was in the days of Napoleon. I think so. He was in Egypt for a while. So Fourier transformation is about expressing some periodic function like step function or sawtooth function in terms of sine and cosine, addition, multiplication of sine and cosine. Okay, it's like converting this undifferentiable pointy equation into pointy function into differentiable like combination of sine and cosine, and it's very beautiful. Okay, it kind of converges. Yeah, Fourier transformation, Fourier series is very very beautiful. And I saw some this pedagogical advancement development in that area, Fourier series, Fourier transform, whatever, because they have this GIF animation movie cartoon that explains it so beautifully in Wikipedia. Okay, wow, beautiful, beautiful. So yeah, even nowadays, some people are doing the right thing in academia. Okay, so it's not all about gays and okay. So some people are still doing the right thing, right? So Fourier, he discovered this Fourier series, Fourier transformation, whatever. Okay, when he was studying heat transfer, to me it rang the bell. Okay, it was like ding 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 ding. Because previously we talked about in the past copium transfer, right? Wow, heat transfer, copium transfer. Wow, I gotta study. I mean, I gotta look at, not study. Oh no no, I gotta take a look at this heat transfer. So I was looking at Wikipedia. Okay, so yeah, click heat transfer, and it was talking about, yeah, in the second law of thermodynamics, yeah, heat transfers from hot object to cold object. Okay, that was very inspirational. Yeah, it's something very commonplace, cliche, simple, common sense. But to me, it was kind of fresh. Okay, and after a break, we'll talk about that. Okay. All right, let's take a break. I'm cooking my dinner, so. Okay, we are back. Um, so, yeah, let's talk about heat. So, okay, the of natural direction of the flow of heat is from cold to hot. Okay. Um, I told you it's kind of I didn't tell you yet. Now I'm telling you. It's a little bit loaded subject, okay? Because we gotta talk about didualism, okay? It's a dualism inside of dualism. There are four components in didualism, okay? Okay, let's start with physics, okay? Because it's simpler, all right? You have some hot thing, so it's up there, higher energy, and hot air goes up, right? Because its density gets kind of sparse when air heats up. What is a heat? It's a kinetic energy of molecules. Okay, so heating. Let's say there's fire. Okay, what fire does is this. So you're burning woods, dry woods, dead woods, okay, fallen tree, whatever, dry woods. You put them in the fireplace and you light it up with matches or newspaper, newspaper and lighter or whatever, right? And then this carbon bonding, covalent bonding between carbons is carbs. So fire and our food, it works the same way. It's all about this chemical bonding energy, covalent bonding energy of between these carbon atoms. Okay, it's a high energy bonding. Okay, and then there comes oxygen, and it becomes low quality, low energy bonding. Okay, so high energy bonding and low energy bonding. The difference between those chemical bonding energy, that's the heat. Okay, it's chemical energy. Okay, and then it becomes kinetic energy between molecules, air molecules or water molecules, whatever, solid molecules, whatever. Okay, so solid molecules in a solid like this, it start to vibrate, because they cannot quite break away, unless you like burn it. Okay, it heats up. It's all kinetic energy, movement. Okay, water molecule, air molecule, yeah, it works the same way. Okay, so heat is nothing but kinetic energy of molecules. That's what heat is. So when air heats up, molecules, they go crazy, right? Just excited. They get high. Okay, so they move around like this. That's heat energy. Okay, so they collide each other, these air molecules, so they tend to expand. So the density become sparse. The density get lighter. That's why hot air goes up, cold air goes down. With cold air, they're kind of like us. You cuddle together, cuddle each other, cuddle up. So they kind of shrink, static. So they're not moving very fast. Cold air, it becomes denser. That's why it goes down. Okay, so you hot air. Well, you know what? Now that we have brand new set of pens, let's color it. Okay. Okay, hot air goes up. I know it's boring now, but once we make some analogy to human world, it will get very interesting. Okay, so stay tuned. All right. So that's air. Okay, hot air, cold air. Okay, hot stuff, they go up. You already kind of know this, probably, where I'm going with this. Okay, cold stuff go down. Okay, so yeah, in human world, let's say you're a very beautiful girl. Yeah, you get picked up by the big corporations or big government agency like Washington D.C. You go. Have you been to Washington D.C.? Have you been to Los Angeles? Have you been to New York City? There are a lot of pretty girls in those cities. Okay, so, yeah, they got picked up by this high-paying jobs just because they are very beautiful girls, tattoo-free, piercing-free, slender, young. Okay, no matter what race you are. Yeah, they get they get very high-paying jobs just because they are very beautiful girls. Okay, and for the rest of us who are not very attractive, we get cold shoulder. We don't get high paying job, okay, because we are not that attractive, okay, including myself, okay. I don't make much money. I try to look nice, but I'm not a girl, first of all, okay. So I'm Asian too. Oh, I told you it's gonna be funny, huh? That's that, okay? And we're gonna take a brief break because we don't want to get too excited, okay? So I'll be right back. I gotta tend my microwave dinner. So. Oh. Okay, we are back. So we made some contribution to physics, mathematics. Okay, we did them a big favor. Okay, at least in a pedagogical, instructional, educational level. Okay, it may not be a big discovery, but we pointed out what they were missing in this physics and mathematics education, this curriculum. Okay, yeah, we are doing them a big favor. Okay, we pointed out what they missed and something very important of great importance. Okay, all right. So now it's time to have some fun with humanology. Okay, so welcome back to humanology. Okay, so I know this kind of like hand gesture. It kind of like looks like President Trump. I was a huge fan. I watched a lot of his speeches and whatever. Yeah, I learned a lot from him, including some of the gestures. I don't comb over. I blow over with the hair dryer and hair spray and whatnot. Okay. So okay, you have got some hot girls. Yeah, they go up. They get hired by big corporations. They get paid a lot of money just because they are very beautiful girls. Okay. And the rest of us, we get cold shoulders. I apply to big corporations. I get turned down. I apply to Ivy League schools, like top schools. I got turned down. Okay, so yeah, I'm you. You are me. Most of you. Okay, I'm very average kind of guy. Okay, I'm no elite. Okay, do you think I'm smart? Well, aren't you? I think you are smarter than me in many ways. Okay, so um. Okay, okay, hot girls, yeah, they go up in this food pyramid. Okay, yeah, hottest item in the aisle on the shelf. Yeah, only the richest person can get purchase those hottest items in the display. Okay, the most beautiful items, yeah, they get priced very high. So only the top dogs, fat cats, can purchase, can afford those most desirable items in a shopping mall, in a grocery store, because they got money. Okay, rest of us, we go to Walmart. We get Chinese products. Okay. I told you it's gonna be funny. We are dealing with humanology, with humor and jokes, and it's a human world. It's not cold objects world like we've been dealing with in physics and mathematics. Okay, yeah. So it's time for something warm, something with humane, something that has to do with our human world. Let's get back down to earth, from all this abstract heavenly celestial body stuff. Let's get back down to earth. Let's be human again. Still talking like a President Trump, man. Oh boy. Okay, so. Alright, so now. So that's aerodynamics, this air molecules, okay? So now, that's air, okay? Air, gas, or fluid, liquid. Yeah, fluid is both gas and liquid. You have vapor, water, ice, right? Fluid means both gas and liquid. Vapor and water, okay? Now we'll deal with solid, rock solid, okay? It works like this. I learned. It's commonsensical, but also something I learned in school. long time ago. You cold object, okay? Ice cube, whatever. And you have hot or warm or room temperature object, okay? Hot. According to second law of thermodynamics, yeah, of course, this direction of energy, heat energy. These guys are just sitting there, okay? They are solid. Hot ice cube, cold ice cube and hot rod, hot metal, okay? These guys are running or vibrating. Yeah, they are vibrating because they are solid. They are not liquid. They are not gas. They are not swimming. They are not flying or running around. No, they're like vibrating. Okay, because they are solid. Still, covalent bonding, chemical bonding is not broken. Okay, they're just doing this. Very hot, cold, sitting very still. Okay, so this heat is kinetic energy, molecular kinetic energy. That's what heat energy is. Okay, just kinetic energy in molecular level. That's what heat energy is. Temperature. All right. Warmth, hotness, or lack thereof, coldness, coolness. Okay. So yeah, this all this. These guys are sitting tight. These guys are vibrating. So yeah. Okay. Energy transfers from high energy to low energy. Okay. Now. Oh, boring. Oh, physics, objects. Oh, who cares about that? It's not fun enough. That's why not everybody want to study science because it's not interesting enough. Okay. But in humanology, well, nobody's watching this, but perhaps in the future, perhaps everybody want to study humanology. Okay. Perhaps everybody will want to study this humanology. Okay. Because it's a lot of fun. Okay. So it goes like this. There's a man. A man, okay? Like me. Loser. Total loser. Like low guy. But yeah, we're a natural guy, okay? Heterosexual natural guy. Because I almost said gay. No, guy. Not gay, but guy. Natural guy, okay? Total loser like me, okay? Like without any money, no social status, no nothing, no popularity. I got nothing, okay? And I'm not coming in contact with a girl, hot girl, but we happen to be in the same grocery store. Most likely, I never get to see them. Why? Because I go to dirt cheap restaurant. Oh, sure, dirt cheap restaurants or dirt cheap grocery, dirt cheap supermarkets. Because I got no money. Good-looking girls, they have rich parents. Okay, they dress nice, but I dress nice, but it's all from second-hand store, so. At least I try to dress nice. Okay, so if I go to a grocery store or restaurant, probably I don't get to see any hot girls, beautiful girls. Then when do I get to see them? Maybe on a highway, on the road. I'm driving and it's stoplight, right? Red light, okay, in the intersection, and I look around. Oh my goodness, look at that girl. And then she be like, she does not like my stare because I have this smell of poverty. She knows. Girls know. They have sixth sense. I do too. Even though I'm not a girl. But I'm a humanologist. So yeah, I know those things, okay? She knows I'm poor man. Although I try to dress nice, but she can smell metaphysical stench of this poverty that I have. Oh, you pretend you are rich, but I can smell your poverty. I know you are just pretending because you look cheap. You're a penny pincher, aren't you? I'm supposed to use feminine voice. You can you can run, but you cannot hide, like President Bush Jr. said. You may pretend all you want that you're a rich guy, but I know. I can smell. You're a poor man. You're fake. You just look cheap. I can smell it. You cannot hide from me. I'm like, okay, well, yeah, you're right. I'm just faking it. Okay, so she does not like the fact that I'm staring at her. So, but do I enjoy staring at her? Okay, I'm in my car. It's a stop. It's a red light in the intersection. Okay, then there's this girl, very beautiful girl. Let's say she is like Asian girl. Okay, slender, tattoo free, piercing free, young, single. Asian girl right there. Okay, yeah, she's in her own vehicle, like more Mercedes or Lamborghini, whatever. Okay, she's a very pretty young girl. Okay, and let's even say she's a virgin too. Okay, college educated, college graduate, making a lot of money. Maybe she's smart too. Okay, I'm looking at her. Oh my goodness, what a beautiful girl! I enjoy watching her. I'm enjoying this. I mean, I'm not looking at her legs or breasts or anything. Just her face, her hairstyle. Because I'm in my car, she's in my car. We are in this stop, this traffic light, red light. It's a long red light, so I know that she knows that. We are kind of towners. She's like, I'm enjoying this. I'm enjoying watching this, absorbing, and making my memory, Woo! I'm enjoying watching her. And she goes like, ew. Because you're a poor man. I don't like you staring at me. If you were a wealthy man, then I would have enjoyed you observing me, staring at me. I would want it you, a wealthy man, would be staring at me. I would want that. I would enjoy that. But now that you are a very poor, penny pinching guy, I don't want you to stare at me. So I'm gonna stare back at you like I'm gonna give you my meanest, bitchy face. Like, so I have because I want to let you know that I hate you. I don't appreciate you. I don't want you to look at me. So I'm gonna make face like so that you understand and know that I don't like you. So I'm gonna stare at you back like I don't know. Okay, so yeah. So you got the idea. Okay, so we have 15 minutes left. I guess I'm getting too excited. Okay, so we're gonna take a break and we get back to this. Okay, so no matter what the fuck we are doing here, okay, we get back at it. All right. So, oh, I just stepped on my coat. Oh, my coat is very long. You know. We get back. Stay tuned. Oh boy. Okay. So how much we have 8 minutes, okay? So yeah, so it goes like this, okay? So let's erase all this. Okay, let's get serious now. Well, before we get serious, let me get some drinks. We have 7 minutes left, so we have enough time to for me to pour myself some drinks. Come on, hello, give me a break. Come on. We'll do dualism, okay? Because it's very important concept. Okay. Dualism is a model of exchange model. Okay. You see it in the logo of Coca-Cola. I mean, not Coca-Cola. Pepsi-Cola. Pepsi-Cola logo 20 years ago, or Tai Chi symbol in China, or Korean flag. Okay. Dualism. All right. So it goes like this. Okay. It goes like this. Okay. Okay. Or you can draw it like this. All right. So plus this long and short, plus minus, minus plus. Okay. Yeah, that's how it's drawn. So it goes like this. Again, we talked about this too many times. Okay. I don't like mixing drinks. Cocktails, I don't like cocktails. I like pure vodka or pure whiskey with some stuff in there, like plant. This, what is this? Willow tree branch, okay? I'm not gonna mix it, okay? Oh, no, that's a no-go. No way. Let's say this cup is full of water and this cup is empty, okay? If I pour this cup full of water into this empty cup, just for you, I'm gonna mix it a little bit, okay? Like this. Cup full of water and empty cup, okay? Ooh, okay? When that happens, yeah, water from my right side transfers to the left side cup. But that's not the end of the story. At the same time, the empty air, the empty space in my left cup is transferring to my right cup. Okay? Because you have two cups, okay? Full of water and empty cup. Okay? If I pour down this right side cup to my left side empty cup completely, my left side cup is full of water, but my right side cup is full of emptiness. So the emptiness transferred from my left cup to my right cup. Just at the same time, the fullness of water transferred from my right side cup to my left side cup. Okay? So it's a simultaneous transaction of positive copium and negative copium. Okay? Here, plus go from up to down, minus the lack of plus goes from down to up. Okay? Like in a market, you go to Walmart, all right? I pick up an apple. Okay, so Walmart now have one lack of apple because I took it. Me, I have one more apple because I got this from Walmart. Now, what Walmart got from me is the emptiness, lack of one apple, absence of one apple. That's what Walmart got from me when I picked up this apple and took it, placed it in my basket, shopping basket. I got the apple from Walmart, and Walmart got one absence of apple, minus one apple. That's what Walmart got from me. When I picked it up, this apple from Walmart and put it in my basket, shopping basket. Okay? That's this transaction right here. But of course, that's not the end of the story. Why? So this is apple, okay? Plus apple. Absence of apple. Okay? Minus a. Then I go to counter and I give Walmart $1, okay? $1 plus $1. Go to the Walmart. Now, in this half transaction, Walmart give me absence of $1. Okay? It's very important to understand. Alright? I gave Walmart $1 in return at the counter, okay? To cashier, right? And what Walmart give me is this piece of paper receipt. Yay! Here's your receipt. This apple belongs to you. It's like title, ownership of this apple. It proves that this apple is mine. Nobody else can touch or eat this apple without my permission. It's exclusively mine. It's property, private property of mine, this apple that I purchased from Walmart. Okay, so it's that. Okay, absence of $1 transfers from Walmart to me. Okay, I have one less dollar. Okay, we are running out of time. Okay, we continue this tomorrow. Okay, thank you. Bye.